In Netflix's three-body problem, the sky behaves like it's haunted. 3 suns trade places, and a planet swings from mild spring to furnace to deep freeze. The show calls it the three-body problem, as if it's a curse. The real mystery is older. If gravity is just the pull between big objects, why does adding 1 extra sun turn prediction into guesswork? Picture standing on a frozen lake while 3 friends tug on a rope tied to your waist. With 1 friend pulling, the direction is obvious. With 2 pulling from opposite sides, there is at least a place where the pulls cancel, and a small step away tends to pull you back. Add a 3rd friend at a different angle, and the cancels out spot starts wandering, because the friends are moving too. Each step changes the balance of the pulls. That changes where you slide next. Nothing supernatural is happening. It is just feedback. That feedback is why the phrase three-body problem became famous. It just means 3 big objects, all pulling, all moving. The future is not random, but it can be fragile. 2 nearly identical starts can peel apart until they look unrelated. In the show, that fragility shows up as seasons that refuse to repeat. The story begins in 1687 with Isaac Newton. His gravity rule was a triumph because it let astronomers calculate paths. With 1 big body and 1 small one, like the sun and a planet, the motion locks into a clean pattern. The planet is falling inward all the time, but it also has sideways speed, so it keeps missing the sun. That sideways miss is an orbit, like throwing a ball so fast it curves around Earth instead of landing. Edmund Halley used Newton's rule to predict a comet would return, and in 1758, it did. Nature answered yes. Then the moon refused to stay simple. Earth, moon, and sun are 3 bodies, and the moon's path has subtle wiggles. Those wiggles showed up in measurements, eclipse timings, drifting, and star positions that didn't line up with prediction tables. A reasonable early assumption was that the sun's extra pull was just a small correction on top of an otherwise neat Earth-moon orbit. Sometimes that worked. Sometimes the corrections piled up, because changing the moon's position changes the direction of the next pull. In 1772, Joseph Louis Lagrange found a crack of order inside the chaos. For a small object influenced by 2 large ones, like a spacecraft influenced by Earth and the sun, there are special places where gravity and orbital motion can balance. For 2 of these spots, a marble in a bowl picture helps. Nudge the marble and it rolls back. The other 3 are more like balancing a pencil on its tip. They look still but don't pull you back after a shove. Lagrange predicted all 5 such regions. Later, telescopes found swarms of Trojan asteroids clustered near 2 of them in Jupiter's orbit, right where the calculations said they could survive. Today, the James Webb Space Telescope stays near another, using tiny thruster burns to hover in a stable geometry. So why isn't every 3-body system tame? Because Lagrange's points are rare safe harbors, not the ocean. In the late 1800s, King Oscar II of Sweden offered a prize for anyone who could prove the solar system was stable forever. Henri Poincaré took the challenge and found the opposite of a proof. He found 3-body motion that never exactly repeats, and he found extreme sensitivity to starting conditions. That phrase just means this. If the initial position is off by a hair, the future path can be off by a mile, given enough time. The equations are deterministic. Same start gives same result, but real measurements never give a start with infinite precision. A quick estimate shows why this is not just a math complaint. Suppose a planet's position is known to within 1 meter. Now imagine the system is such that this uncertainty doubles each orbit. After 1 orbit, the uncertainty is 2 meters. After 2 orbits, 4 meters. After 10 orbits, doubling 10 times turns 1 meter into about 1,024 meters, roughly 1 kilometer. After 20 orbits, about 1 million meters, about 1,000 kilometers. After 30 orbits, about 1 billion meters, around 1 million kilometers. Bigger than the distance from Earth to the moon. No randomness. Just amplification. The same 3-body amplification shapes the universe on bigger stages. In dense star clusters, close encounters act like gravitational pinball, often flinging one star out and tightening the remaining pair. Astronomers catch the aftermath by measuring star speeds in clusters. Some pairs are suspiciously tight, and some single stars are moving too fast to have been born that way. On a smaller scale, space agencies do it on purpose. A gravity-assist flyby is a controlled three-body interaction where a spacecraft steals a little motion from a planet's orbit, changing course without much fuel. Modern astronomy lives with Poincaré's lesson. Many stars are in pairs or triples, and planets have been found there too. An open problem is drawing the exact border between stable and unstable. A planet can look fine for 1 million years in a simulation and still be doomed on longer timescales. Observers keep measuring real systems by splitting starlight into a spectrum, a rainbow of colors, and watching characteristic lines shift back and forth as a star moves. Planets show up as tiny dips in brightness when they pass in front. Then theorists rerun the same system with slightly different starting numbers to see how often it survives. Even the solar system, pushed far into the future in computer experiments, shows a spread of possible outcomes. So the bleak calendar of Netflix's three-body problem has a real backbone. 3 suns do not need magic to create a world that can't plan. The same gravity that makes an apple fall can also make long-term prediction impossible. Not because nature is lawless, but because nature is exquisitely lawful and brutally sensitive. If 3 bodies can already blur the future, what happens in places where thousands tug at once, like the core of a galaxy? Like if this was interesting, hit the subscribe for more and turn that notification bell on.